Hi everyone, my name is Kilian. I work at CA in a storage group. I'm a systems administrator for file system. And I will talk about the way we monitor our Lustre usage at CA, how we try to make sense of what users do on those file systems, and how we try to keep on top of things. So a bit of motivation behind this. Lustre monitoring is hard, notoriously so. Very few tools are available to monitor the states of your file system, and on top of that, Lustre is a distributed file system, which means that the stats are distributed also. They're spread everywhere on different servers, different files, on clients, so it's kind of difficult to get a big picture idea on what's going on in the file system. Usually, an administrator needs stats for several reasons: to check that everything is running smoothly, to analyze problems when they appear, and to watch users, because sometimes they do things which are not good for the file system. And also because we like stats and we like graphs, and that's a cool thing. So at CA, we need some tools to do that. First, to monitor the file system activity in terms of performance, trends, evolution, and so on. And also to understand the file system usage, like the typology of our files, the different kind of files, the repartition in terms of size, and that kind of thing. And also to get an idea on what files the users are working at a specific time. What volumes it represents. That's what we call the working sets. So the current state of Lustre monitoring, presently a lot of logs, text files, stats files spread everywhere, so it's not very easy to make sense of that. That's what we are, and what we want is more something like that, like some control, some graphs, image, pictures, something that makes sense. We're not there yet, but we're working on that. So, what do we talk about? First, how we monitor the file system activity. With the tools we use, what we do to visualize the real-time activity. We talk about bandwidth, metadata operations, base usage. Also, how we diagnose slowdowns, unexpected behavior. I will show an example of how we can suggest improvements for user applications, and also how we understand how people use their files. So we use something we call the file system temperature, which basically visualizes the working sets of the users and their evolution. And then I will try to illustrate how we use some tools to answer typical questions like, I don't get the speed I expected from the file system, my LS is too long, can you give me the current usage for each user working on this project, and what kind of data is in the file system, so that a lot of typical questions we get, and we develop tools to answer that. And a little disclaimer, everything I present is for Lustre 2.1, so you may have different experiences using different versions. The stats may be not in the same place. So, how we monitor the file system activity? First, our toolbox. So, we use different kind of tools. I will just present a few of them. The Lustre admin tool belt, the basic tools that any Lustre administrator probably already know and use every day. So there's LTOP from NMT, so the Lustre monitoring toolkit, I think, which is developed at Livermore. LTOP is really useful. It's a top-like command to get instant stats about the file systems, like bandwidth for each OST, segregated set for OSSs. You get metadata rates, each kind of metadata operation, IOPS, and so on. So it's really like top for Lustre file system. It's really great. It uses a network of daemons running on each server, gathering the stats and putting everything together for an aggregated view. So that's really convenient. We also use Collector. This one looks like SAR or DStat or any tool like that. It allows you to monitor the infillment traffic, Lustre activity, and clients, OSSs. That's very interesting too, to diagnose things at the server level. So there's no aggregated view, but that's still very useful. And we also use the standard utilities for Linux administration like htop, dstat, and all that. We also use a lot the open source tools we developed at CEA. First was this Shine. It's a command line tool for Lustre file system administration configuration. So you can configure a file system with a declarative configuration file. You can describe the file system very easily, and then you can administrator it like start the server, mount the client, stop the servers. So it's very convenient. Everything is centralized on one server, and the commands are distributed on all the Lustre servers. So it's really a time saver for Lustre administration. The second one is Robinhood. So you may be aware of it already. It's a policy engine for file systems in general, but it's really adapted to Lustre. It has specific features for Lustre, so I will talk a bit later about Robinhood in more details. And it's really useful for large file system management. And on top of that, we developed custom scripts to consolidate all the data we gather from all these tools. And we do some scripting, batch scripting, and Python scripting around that. Basically, we parse ProCFS Lustre a lot to get the stats. And we do graphs too, because we like colors, and we use RD tool for that. It's really the most convenient tool. Convenient, maybe not the right word, but it produces the best results for our needs. So, a word about Robinhood. It's really a Swiss Army knife for your file systems. The main features are auditing, accounting, auditing, migration, purge. Everything you can want to do on a file system, you can do that based on policies. So it's massively parallel. And the main idea behind Robinhood is to give you an accurate representation of your file system, your file system metadata in a SQL database. The main advantage of that is that you can get very fast reports on your file system usage. And you can do all sorts of actions on the file system without having to query the actual metadata on the MDS. One nice thing it provides, for instance, GU and find replacement that will query the database instead of querying the file system, so it's much faster. It also provides advanced capabilities for Lustre file system. It has knowledge of OST repartition of your files, indexes, objects, so you can purge old files based on OST, so it could maybe answer some of the questions from the previous talk. You could also list files per OST. It's aware of pools, Lustre pools, so you can define all sorts of policies based on OSTs or pools locations. And the main interest about those specific Lustre capabilities is that you can register as a changelog reader for your file system, so you don't need to scan the file system once it's installed. You can just get all the updates from the file system through the changelog in real time in the SQL database. It also comes with reporting tools, CLI, and a web interface. It's open source, and you can download it on Robinhood.sourceforge.net. So at CEA, we use one instance of Robinhood per Lustre file system, and we use changelogs a lot. This is what we use to monitor the file system, the activity on our file systems. So it's kind of dashboard with an overview of what's going on. So we have a vertical view. Each column represents one file system, so we can correlate events happening on a different area. So, for instance, on the first line, we have bandwidth here. So, writes are in red, reads are in green, and below that we have the metadata operations. It's MDS RPCs. So, for each file system, we can correlate a peak in RPCs with a peak or no in bandwidth, so it gives us some information. We also have the number of clients mounted on the file system. In another view, we have some Robinhood information, the volume of each of our file systems, the number of inodes, and so we can keep a look on the evolution of the usage of the file system and on what's going on. A little more details about the bandwidth graph. We use information from PowerKFS, Lustre, BD filter, name OST, and stats. We use read bytes and write bytes to get the bandwidth information. We get that on each OST, and we aggregate all this information into one graph to get really the overview of the file system. And so we get one graph per file system. So that's two illustrations. We see that this one is mainly reads. Here it's more balanced with peaks and reads and systemic writes. We use almost the same thing for metadata. So we graph the number of RPC of each type. We get that information in PowerKFS Lustre MDT, FS name MDT 0. So for instance, for now it's just one MDS, one MDT. And the information we want is in the stats file. So what we use is a number of OBD ping, which gives us a file system health. So it's helped us in the past to diagnose some problems we got with nodes. We also graph the number of connect and disconnects, so we can visualize nodes mounting and unmounting the file systems. We graph MDS get RTTR, XFTTR, so we can visualize the peaks in attribute reds, which are typical of file copies or things, this kind of things. We also graph the MDS stat.fs, MDS read page, which gives you an idea of the number of read deals the users are doing. And LGMI bits and queue and MDS close, which gives us a representation of the number of open and close in the file system. So to illustrate that, we have two kind of graph on different file systems, which have the same number of clients, 6,000, but different usages. On this one, that's a long-term storage file system, where we can find large files, and we see few metadata operations, like in the hundreds. On this one, on the other hand, that's a scratch-like file system. We see a lot of opens and peaks up to 30,000. So, same number of clients, about the same size, same range of size, but very different activity, very different usage. Those tools of graphs, they help us diagnose problem, and for instance, we can diagnose slowdowns happening on the file system with that. So first, we can go from a graph to identifying the clients responsible for those misbehavior. What we do, we detect peaks on the RPC graph. First, we did that manually by just watching the graph and seeing when the peak was happening. Now we do that automatically by averaging the last 10 values in the RD2 database, and we compare that to a threshold, so that can give us alerts. When we receive such an alert, we try to collect RPC samples. Same way, it was initially a manual process to enable debug traces. collect those traces and disable the debug traces to go back into production. No, we do that automatically also. We automatically collect automatically collect traces in the background for 5 seconds every 5 minutes, and we keep 7 days of logs. That allows us to get back in time and be able to analyze the traces for any event we can see on the graph. So, for instance, here, with a peak in MGS get exottr, we run our scripts on the traces we collected for that time frame here, and it gives us the name of the IP of the nodes involved, the need information, the count of RPC for each node, and the details of the RPC, the type of RPC. So we see here it's a total match between the graph and what we get, and the get exottr is very high for those 3 nodes. So we have 3 clients which are responsible for that. Then we can go to the scheduler to see what job is running on those nodes once we have identified the clients. And we get the jobs running on those nodes and the user, so we can now contact the user asking if it's an expected behavior or not, and see with the user if we can do something to correct that. For instance, we had a case where we were able to S-trace the process responsible for this behavior, and we've seen such things that displayed here. So basically, the code was looking for a stop file in the job directory for every iteration of the simulation, and so we concluded it was not a good way to stop a simulation. So we contacted the user and suggesting him better ways to stop the simulation. So this is what we call the file system temperature. That's another example of graphs we use. We represent here the working set of our users on the file system range. So that's basically the set of files which are recently written or read. The negative values are the volume accessed, the positive values are the volume modified. So we can see that that's the data production and the data in use. And each color represents the age of the file. So the cold colors represent the old files, the cold data, and the hotter colors represent the data more recently accessed or produced. So we see, for instance, in that graph that 70% of data produced was produced in the last 2 months. And here that 80% of the data was accessed less than a month ago. So that gives us a representation of what users are doing in the file system. You can see here that there are some big red bursts, for instance. And it allows us to better understand how the users access the files. How it's done? Basically, for each file in the file system, we compute its age, whether it's its modification or access age by just subtracting the last modification or the last access time from the current time. We aggregate that by count or volume, by age range, and we do that based on the Robinhood database, so we don't need to query the file system for that. It's an optimized SQL query, and it could be kind of slow for large file systems. So we try that for file system up to 100 million file nodes, but over that it's kind of difficult. So we may need to improve the process. There's some other magic involved. There's a big command line to generate the graph. It's about 6,500 characters long. But at the end, it produces an interesting picture. The main benefits of that is that we can visualize the current working set of the users. We can see, for instance, if they just produce files once and they don't touch them anymore, or if they currently, or if they read the same files over and over. So it gives us a lot of interesting information. And it also allows us to anticipate file system evolution, mainly in the term of sizing. For instance, if we see that the data is most recently written data, we need to expand the file system. If it's never touched or very old data mainly, we could purge some old files and regain some space. It's useful. Some examples. Here, it's a graph in volume where we can see significant reads and writes. Here we can see the cooling effects after a large read. So here's a read, it's recent, and then after some time the files are not touched anymore, so the colors get colder. This one shows a file system which is mostly red, and the data produced is kind of old, so it gives us information on the characteristics of file system usage. And this one is a graph in inodes. It shows us actually the drop of the database in the Robinhood tool. So we removed the database and we restarted the scan again from 0 in the file system, which has 50 million inodes, and we see the scan is pretty linear. It took 2 days to scan 50 million inodes. So that was an interesting way to visualize a Robinhood scan. Next, I will show you quickly how we can answer some typical questions we got about the file system, and that's pretty much a Robinhood cookbook that illustrates what we can do with Robinhood. First question: a user comes to you and say, I don't get the expected gigabyte per second. When I use my code, I don't get the expected performance. At TA, we have different file systems for different usages. The user documentation usually indicates the recommended file size for each file system and what the purpose of a file system is. We also talk about purge policies, quotas, and so on. And often when those recommendations are not followed, it results in bad performance for the user. Usually that's the case of small files. User writing large amount of small files in these directories that can have a great impact on performance. So we usually answer that writing branch block is more efficient, and that metadata overhead decreases performance. So what we do about that to avoid those kind of problems, we implement file system quotas, typically in a number of inodes. So usually a limited amount of inodes motivate the users to write bigger files. And we also do a lot of user guidance. So we try to document as much as we can the usage of the file system, and we also do file size profiling to detect the small file in the user directory, and we use Robinhood to do that. So this information is provided to the users if necessary, and we try to help them take appropriate measures to resolve those problems. So the file size profiling is made with a Robinhood database. It's available in the web interface. We can have summary per users, and the rules we implement is that when a user doesn't match our policies, we send informational emails. So the thresholds are an average file size under 50 megabytes, more than 80% of files smaller than 32 megabytes. We also give recommendation on good I/O practices, and we have a graduated response system. If the user doesn't answer after the 2 first warnings, the job submission is suspended after the 3rd warning, and then we can also pack the data to make bigger files and to restore a good performance in the file system. So we use Robinhood tools to do those reports. So you can get, for instance, file size profiling per user. For the top users, the users using the most files, having the most files, you can get the average file per user and the ratio of files between in a certain size range. For instance, is between 1 and 31 megabytes. So we see that this user, for instance, is very high ratio. Yes. We also can detect small files by using those RBH report commands. For instance, this one lists all the directories with at least 500 entries, sort by average file size, displaying the smallest file size first. So all those command line tools can be used with a full debug flag, which allows you to see the real SQL request Robinhood is performing, so you can reuse and optimize it or customize it. We also can, I will go faster through those examples. We also can detect large directories, so directories with a large amount of files, because it's usually not good for performance either. Sequential processing of media is usually not very fast. So we can set alerts in the Robinhood's configuration on a DRCOM, for instance, for directories containing more than 10,000 files, and recent one, last modification, smaller than 1 day. And when Robinhood scans the file system, we will send an alert for this kind of directory, so you can point the user directly to his directory. And there's also a command line to get the report of the largest directory in the file systems. Also, Robinhood can be used for accounting. For instance, if you want to get the current usage of each user working on the same project, given that some data of this project is in a specific directory, but users also have some data from the same project in their own directory, and project data can sometimes be identified by a group attribute or any other tag, and be anywhere else in the file system. You can use Robinhood for that. So by using different commands, you can get reports per user in the whole file system, and everything split by a project. So you can see that user 2.1 and for the group project 0.1 has that many files, that much space is used, and so on. So you can get the same kind of report for a project. You can also use RBH DU, which gives you the space used by the user in a specific directory, or by a group. That's exactly the same as DU, but it doesn't scan the file system, it just uses the SQL database. And you can also use RBH find to find files with specific attributes in your whole file system. You can also monitor contents in your file system by giving your files some attribute. You can define file classes in Robinhood, and you can define arbitrary file classes based on file attributes like name of the file, its path, the owner, the group, even the Lustre OST or anything. And you can get reports about those classes, which could be really useful. And you can obviously draft those classes. So, to wrap things up, visualizing file system activity is really useful. We can diagnose abnormal patterns. We can also suggest improvements for user code. And it gives us a better understanding of what the users are doing, their behavior. And we can help them getting the best I/O performance out of their application with that. It also allows us to plan our file system evolution for the next generation. We can see really what kind of space is used, how it's used, so we can size the next file system better. And to do that, solutions exist. You need some assembly. Everything is not coming out of the box already usable, but all the required information is there, whereas in ProcFS Lustre or in the file system metadata, and especially in the Robinhood database, this is really useful. And yeah, you need some more tools to do that, namely Robinhood and some harder to knowledge. Thank you for your attention. Do you have any questions?
So you're gathering some stats, like stats every 5 seconds.
Mm-hmm.
5 seconds, 5 minutes. How much does, what impact does that have on the cost of performance? So that's something that you decided that you would talk about.
Yes. This is in production. We didn't detect any impact on performance. We do actually activate the debug traces for 5 seconds every 5 minutes. And we keep the logs out of that for maybe 7 days. So the biggest impact is that we need to store those logs, which are maybe a few hundred megabytes. And that's pretty much it. We didn't detect any impact in the file system performance, whether it is in metadata rate or... We didn't benchmark it explicitly, but in the normal production, it doesn't impact much the performance.
Yeah, you mentioned that this is running for, or you have this product for 2.1 series of Lustre. Do you have some already experience what will happen if you go to 2.4? Do you have some facts, or this is completely out of your monitor?
We didn't try anything on 2.4 yet. So
do you expect technical problems, or?
I think the only thing we can expect is that some stats may change location, may not be located at the same place anymore, but it's just a matter of updating the scripts to reflect the new location, maybe detect the choose a location based on the Lustre version or something like that. But it's no big impact. The stats we're collecting are pretty standard, like bandwidth, read bytes, written bytes, IOPS. I don't expect that to change in Lustre 2.4. But we didn't try, so maybe we can get some surprises.
One thing I have tried is looking towards finance to the form.
Yeah.
I'm covering this part of the tool for monitoring tomorrow. Am I right in thinking that all of the file in a user usage queries can be done by date as well? Is that right?
Sorry?
So you could query who was using how many files did this user have last month?
Yeah, we can do that with verbiage find, for instance. It takes basically the same attribute as the regular find, so you can find files for the date of modification, last modification, or last access. So yes, we can do that too. And that's kind of what we use to generate the temperature file system graph. Not using the Robinhood command line, but querying the database directly. But all the information is in the database, yes.